Great expectations. We're going to take a look at expected value. So expected value of a variable starts with a variable x associated with a sample space S, is T1 to TR, with a probability distribution of P1 to PR. Recall here S is going to be numerical. It's going to be tags, which are numbers or vectors. That means we may have to do some pre-processing, map the data to a subset of a vector space. And usually that vector space will just be Rn. Then the expected value of x, or E of x, is a linear combination over the vectors in S, where the coefficients of the linear combination are the probabilities in the probability distribution. Or in other words, the sum x equals 1 to r, t sub x, p of x. It's also known as the theoretical mean of x. Sometimes it's denoted by mu or mu sub x. For example, here are 6 outcome of a die, and notice we're going to tag that. Our sample space is going to be the numerical 1, 2, 3, 4, 5, 6. We're going to assume the die is fair, so each outcome is equally likely, so our probability distribution is all 1/6. Our expected value is 1/6 times 1 plus 1/6 times 2 plus 1/6 times 3. This sum, and that's 21 over 6, and that's 7/2, or 3.5. Now this was the average of the sample space, but only because the probability distribution is uniform. An unfair die would lead to a different expected value. For example, let's use another probability distribution. Now 1 through 5 outcomes have a probability of 1/10, and outcome 6 has a probability of 1/2. Our expected value is 1/10 times 1 plus 1/10 times 2, and so on and so forth, up to 6/2, which is 15 over 10 plus 3, which is 4.5. So how do we interpret this number? Well, we're going to build on the axioms until we have a good interpretation. So suppose x is a random variable associated with some sample space S, in this case just on the real line. Suppose f is a function that's defined for each t sub x in S. So therefore we can say a new variable y is a function of x with a new sample space y1 to y sub m, where y sub x is f of t sub x. So this y is a variable just like x is a variable. It just happens to be the image of f applied to the sample space of x. The expected value, therefore, is the sum x equals 1 to m y sub x p of x, which means that the expected value of f of x is x equals 1 to m f of t sub x p of x. So consider the function, say, f of x equals x squared. Here y is equal to x squared. X squared means that our sample space for the function applied would be 1, 4, 9, 16, 25, 36, the squares of the original S. These are instances of y equals x squared. The expected value of x squared would be the sum of all the things in S divided by 6. Notice we're back to our fair die. That's 91 over 6. Equivalently, the expected value of x squared is the sum, x and s, of t sub x squared p of x, which is k equals 1 to 6, k squared times a sixth. Move a sixth out here in front. There's a formula for the sum k equals 1 to n of k squared. Insert that formula. We get 91 over 6. But again, a natural question is, what is an expected value? So we're going to use an axiomatic approach to establish properties of expected values, and then we'll use those to interpret and answer this question. The first property is linearity. So how do we prove linearity? Well, we're going to have a joint probability distribution because we're going to have an x and a y where our sample space S is pairs t sub x u sub y. The expected value of a function is defined like this. And now we can prove our theorem. So we write out the definition. We split it up at the sum and factor out the alpha and the beta. And notice now we are summing over the y in the first sum. That's going to give us a marginal p of x. And we're summing over x in the second sum, which is going to give us a marginal p of y. And now we have the expected value e of x plus beta times the expected value e of y. And there's our proof. So we have linearity, some immediate consequences of linearity. Suppose f of x is identically 1. Then we're looking at the expected value of 1 is f of t1, p1 up to f of tr, pr. But they're all equal to 1. And the sum of the probabilities is 1. So the expected value of just the number 1 is 1. And in general, the expected value of a constant is that constant. And if mu is equal to e of x, then linearity says that the expected value of x minus mu is 0. Now we're also going to look at the variance, which is the expected value of the variable x minus the mu, that quantity, squared. So let's look at some properties for variance. So again, we've got a x associated with a set S with a probability distribution. The variance is the expected value of the quantity x minus mu squared. And we square that, use linearity. And notice that e of x is also mu, so we've got minus 2 mu squared. The last one is the expected value of the constant mu squared, which is mu squared. And so we simplify a little bit, and notice that we've got the expected value of x squared minus the expected value of x, that entire quantity, squared. So there's our first property of variance. What if we had variance of alpha times x? Well, we write out our use our first property. We can factor out an alpha squared, and having done so, we see that we get alpha squared times the variance of x. So the variance of alpha x is alpha squared the variance of x for any alpha in R. So if x and y are independent, then we can show that the expected value of the product is the product of the expected values. So we'll have a joint probability distribution for the x and the y. If they're independent, the joint probability distribution is the product of the marginals. So let's prove our theorem. So we take the expected value of x times y, which is the double sum over x and s and y and s of t sub x u sub y, p of xy, but p of xy is the product p of x, p of y. So now we bring the p of x through the sum over the y, and we've got e of x, e of y. For example, suppose x and y are associated with 0, 1, and half probability for both. In other words, we're flipping two fair coins. The expected value is a half for x, and the expected value is a half for y. If I've got x and y in 0, 1, then the pairs xy are 0, 0, 0, 1, 1, 0, and 1, 1. And when I take the probability distribution for those pairs, it's a fourth, a fourth, a fourth, and a fourth, because x and y are independent. If I take the product, then I'm going to end up with the xy is associated with the set 0, 0, 0, and 1, respectively. So the expected value of xy is a fourth, which is the product of e of x and e of y. So independence and variance, if x and y are independent variables, then the variance of x plus y by our property 1 of variance, it's this. We can square out the x plus y quantity squared inside the first expected value, and we can then use linearity. We can also expand the square of the sum. Notice when we reorganize that we're going to end up with some cancellation because we have the variance of x, then the variance of y, but notice that e of xy is equal to e of x, e of y. So this is the variance of x plus the variance of y. By independence, that last term is 0. So the variance sum law in general says if you've got x associated with some sample space and a probability distribution, and if x1 to xn are also associated with x with the same probability distribution as x, in other words, they're identically distributed, and if x of I is independent of x of j for all I not equal to j, which means they're independently distributed, we get this theorem. The variance of the sum is the sum of the variances. Let's prove it. It's true for n equals 2. We showed that on the last slide. But for the n plus 1 case, we let y be x1 to xn, summed together. Then the variance of y plus xn plus 1 is, by our previous slide, the variance of y plus the variance of xn plus 1. But by our induction hypothesis, the variance of y is the sum of the variances, proving the theorem. Let's look at an example. Suppose you have a random experiment, 1,000 trials, xi is the outcome of the ith trial of the following. Randomly choose either a 6-sided fair die or an 8-sided fair die. The 6-sided we're going to say is green and the 8-sided is gray. Choose one of them at least twice as often as the other. The one you choose most often is your favorite, your preference. Roll the chosen die, record the result. 1 to 6 for the 6-sided die, but 0 to 7 for the 8-sided die. For example, suppose you like the green one. So you roll the green die, and then you record the result. You roll maybe the green die again, and you record the result. And then maybe you roll the gray die, and then you record the result. So observation 1 is of someone who uses the 6-sided green die twice as often as the 8-sided die. So their data looks something like this. In each of the 1,000 trials, she rolls one or the other, but she prefers the green one. So about twice as many rolls with the green as with the gray. Observation I is of someone who chooses the gray at least twice as often as the green, so that we see twice as much gray in observation I. There are two distinct classes. Class 1, those who prefer green, and Class 0, those who prefer gray. Recall that each trial, each random choice of a die and subsequent roll is independent of every other trial in the experiment. So in observation 2, did the 6-sided or the 8-sided die get used more often? How about in observation 14? What was their favorite, the 6-sided or the 8-sided? The answer is actually quite straightforward. We have two random processes. X is the variable associated with the 6-sided fair die, Y with the 8-sided fair die. We have two classes of behaviors. Class 1 uses X twice as often as Y at least, and Class 0 uses Y twice as often as X at least. Note, we actually have two random variables. The expected value is the same as both, and this is not unusual in data science. The average, which we can write either way, for the 6-sided die we get 3.5. For the 8-sided die, we likewise get, remember, the variable for the 8-sided die is y, and the expected value of y is also 3.5. So there's no predictive information from the means. The answer comes from the spread. If mu is the mean or expectation, Ex of x, then the variance is defined like this, as we saw earlier. Six-sided die, here is our variance, 2.91666. For the eight-sided die, the variance is about 5.25. So that means the variance of x is less than the variance of y. In other words, y is more spread out than x. So variance yields the answer. Variance for class 1 is less than variance for class 0. Class 1, the green's used twice as often as the gray, the x twice as often as the y. So the variance of class 1 is less than or equal to 2/3 variance of x plus 1/3 variance of y. That's 3.69. Class 0, y is used twice as often as x, at least. And therefore, we get that the variance of class 0 is 4.47 as a lower bound. So in observation 2, did the six-sided or the eight-sided die get used more often? Well, if you like green, class 1, your variance is less than or equal to 3.69. If you liked gray, class 0, your variance is greater than 4.47. The variance in observation 2 is 3.688, so the favorite die in observation 2 is the six-sided die, class 1. In observation 14, variance 4.496. Favorite die is the eight-sided die. So this is application to user preference. We all have preferences: comedy versus drama, SUV versus sedan, salad versus steak. But such preferences are not equally spread out in general. For example, there's many more ways to eat junk food in our society than there is to eat healthy, especially at lunchtime when you have to just go somewhere and grab something fast. Healthy eaters mostly eat green, but sometimes they do eat gray, and the junk food eaters, well, sometimes they eat green. So let's look at the downtown lunch crowd. 1,000 workers each play My Favorite Die 1,000 times to choose between green healthy lunch or a gray junk food lunch. 500 workers prefer green, 500 workers prefer gray. And the variances is what separates them into two different classes. In reality, however, preference is not purely random. We are often influenced by others. So suppose we played this with workers in groups of 1 to 5, mostly 3 or 4, group selection based on 4,039 node social network. Each rolls a die, and then the entire group goes to the majority vote selection. Well, now we get something that looks like this. Variance alone can't predict preference. But you can see that variance is still useful in this case as an exploratory model. So in summary, this is how we define expected value. It's linear. If x and y are independent, the expected value of the product is the product of the expected values. Variance is an important type of expected value. But to really understand what an expected value is, we need the laws of large numbers, which we'll look at next.